Okay, we're starting our new unit on organic chemistry. We went over some basic organic chemistry last year, so we'll just kind of continue on. And this first lesson will be basically a review of what we did last year. Okay, so again, the definition of organic chemistry or organic compounds is those that which carbon atom is nearly always bonded to uh, another carbon atom or to hydrogen or to a couple other specific elements such as oxygen, nitrogen, sulfur, or phosphorus. Basically, organic chemistry is the chemistry of carbon. So carbon's going to be our main base, and then different things will bond to it. Okay, there's millions of different organic compounds. The way they go together and the way they orient changes each one. Okay, so some carbon-containing compounds such as carbonates, cyanides, carbides, and other oxides of carbon are still classified as inorganic. Again, so you have to know the difference between organic and inorganic. The biggest and easiest way I find to remember, okay, is that all ionic compounds, so like carbonates, cyanides, and or carbides, are all ionic, part of ionic compounds. So no ionic compound is classified as organic. Okay, really the only molecular compound that has carbon and oxygen is the oxides of carbon, so CO2 and CO. These are inorganic. So they're the ones that you kind of have to remember. The rest kind of fit into that category of ionic. Okay, and all compounds that contain no carbon atoms are inorganic, which again, so like when you're looking through and if you're trying to find out if it's organic or inorganic, you first look, does it have carbon in it? Is it molecular? Is it an oxide? And if it doesn't fit in any of those categories, so it has to have carbon and then it's bonded to H's or other things like that, or if it can have, as long as it's not just carbon and oxygen, so if it was like CH2O, something like that, that would still be organic. So like the oxides of carbon only mean carbon dioxide and carbon monoxide. Okay, special nature of carbon atom, one of the reasons it can make these millions of different compounds, okay, is because, okay, first it has 4 bonding electrons. Okay, so really only carbon and silicon have 4 bonding electrons. Carbon can form a strong single, double, or triple bond with itself. Carbon atoms can bond together to form a variety of geometric structures, so they can be put together in chains, rings, sheets, tubes, spheres. Again, each of these structures is an allotrope, which means it has different structural modification of an element of pure carbon. Again, so like diamonds and graphites, both made of graphite, both made of carbon. Okay, but just the way that they're kind of put together changes what they look like overall. Okay, classifying organic compounds. So in general, it is the nature and location of the chemical bonds that determine the chemical and physical properties of those organic compounds. So we can use structural similarities, or by using structural similarities, chemists have organized various organic compounds into what we kind of call as their families, or their general, and those families have the general same chemical reactivity. One classification scheme presented below kind of uses structure and type of atoms present. So we have organic compounds. Okay, they can be split into hydrocarbons, which only contain carbon and hydrogen, and hydrocarbon derivatives, which we'll kind of talk about later, alcohols, carboxylic acids, esters, okay, and so on. Okay, from the hydrocarbons, we can split into aliphatic hydrocarbons. Okay, these do not contain a benzene ring. Okay, and we'll talk about what benzene is later. And aromatic hydrocarbons, which are based on these benzene rings. And then aliphatic can be split into alkanes, alkenes, and alkynes, which we talked about last year. The alkanes only have single bonds between carbon atoms. Alkenes will have a double bond between carbon atoms, at least one double bond, and alkynes will have a triple bond. Okay, so we'll look at kind of starting with hydrocarbons. Okay, they're compounds containing only carbon atoms and hydrogen atoms. Okay, so examples, coal, oil sands, heavy oil, crude oil, all those are kind of different types of hydrocarbons. Okay, refining is the technology which uses physical and chemical processes to separate complex mixtures into simple mixtures, and we'll talk about that more in chapter 10. Okay, so kind of just looking at some different fuels, okay, in extraction. This is out of your textbook. You can kind of go through and read it if you need to. Okay, some properties of organic compound or for organic compounds. Really, organic compounds are molecular compounds, so their properties are going to be very similar to molecular compounds. Okay, when we compare them to inorganic, again, inorganic, they can be ionic or molecular, and so like comparing them, usually like when we're comparing to ionic, there's going to be a big difference, but they'll be similar to some molecular compounds. So the bonding, they'll have covalent bonds, okay, where like in this case, most are ionic, some can be covalent if it's a molecular compound. Okay, polarity, so they can be non-polar unless we add like oxygen or something that would make them polar. Okay, and like for example here, C3H8 would be non-polar. Okay, for the example here, sodium chloride would be ionic. Okay, the melting points are going to have fairly low melting points. Okay, so negative 188. Okay, compared to sodium chloride, which is like 801. Okay, boiling points, again, low. A lot of organic compounds can even be a gas. Like this is propane. It's a gas at room temperature. Well, it's a gas anywhere above negative 42. Okay, to turn sodium chloride into a gas, you have to heat it up to 1,413 degrees Celsius. Okay, the flammability for organic compounds, lots of them are highly flammable. Okay, they burn in the air. Okay, and so like propane, that's what we use in our barbecues. Okay, just a small spark will light it up. Okay, where organic or inorganic compounds, lots do not burn. Okay, solubility, it kind of goes back to likes dissolve likes. So most are non-polar, which means they're non-soluble. Okay, and most inorganic compounds are soluble because again you have those poles. Okay, and then particles in a solution. So if we put them in a solution, these like molecules stay as molecules. Okay, these would break apart into their ions. Okay, and so kind of learning check like some different things you should be able to label, like is it organic or inorganic? Okay, so like does it have a high melting point? That would be inorganic. If it's not soluble in water, okay, overall kind of organic is not soluble. Has the formula C3, CH3, CH2, CH3, so this would be organic. Okay, it has carbons and hydrogens, and that's it. Okay, formula has, well, is magnesium chloride. Okay, there's no carbon in it, so it's inorganic. Okay, and it's also ionic compound, so it's inorganic. Okay, burns easily in the air, that's organic. Has covalent bonds. Really, that can be both, but like all organic compounds have covalent bonds. Only some inorganic have covalent bonds. Okay, so now looking at our aliphatic hydrocarbons. Okay, we're going to look at the three different types. So we kind of did these last year. We started with the alkanes. So alkanes are the simplest of the hydrocarbons. They only contain single covalent bonds. Their general formula, okay, CnH2n plus 2. So like if we know how many carbons, so in this first one, if we have one carbon, okay, H would be 2n. So since we have like the whatever number goes here, so we have one carbon for methane. So we'd have 2 times 1 plus 2 equals 4. And you can see here we have 4 hydrogens. And so if the alkane contains 5 carbon atoms, so it'd be C5H2 times 5 plus 2. So we get C5H12. Okay. Oh, that's covering up some of the things. Okay, organic compounds that only have single bonds, no double or triple bonds anywhere, are called saturated because every carbon atom is bonded to as many other atoms as it is possible. Okay, any set of molecules that differ by one specific unit, such as like a CH2, so like in the middle here, these are all CH2s, okay, is called a homologous series. Thus, alkanes form a homologous series. So like this series would be methane, ethane, propane, butane, and you can continue on. There should be a U right there. Okay, so modeling alkanes or modeling really any organic compounds, we have different ways that we can represent organic molecules. So the first way is the empirical formula. So empirical formula is just basically tells us the type and numbers of atom present. So C5H12. Okay, it has no attempt to identify like the structure or like if is it all in a row? Does it have branches coming off? Okay, so it's not very useful for most applications other than just to tell us how many carbons and hydrogens are in it. The expanded molecular formula, okay, now shows the groupings of atoms. Brackets are used to indicate the location of branches, okay, and in the formula to the left, so a side chain consisting of CH3 is shown to attach to the second carbon. So we have CH3, CH. This CH3 is branching off of this second carbon. So that's why we use the brackets there. Okay, and then CH2, CH3. Okay, the structural formula, now basically we're taking this expanded molecular formula and actually showing each bond and what it looks like. So this is the same molecule. Well, actually, all of these are the same molecule. Okay, just different ways to show it. So the structural shows like a clear picture of all atoms and the locations of every bond. Straight lines represent chemical bonds between atoms. Okay, and although it is detailed and accurate, it requires a lot of space, a lot of writing. You've probably done some of this, or you did some of these last year. Okay, make sure like when you're working through your assignments and doing your drawings and stuff, okay, it'll say like draw structural formula, draw the molecular formula, or draw the condensed structural formula. Make sure you know which one. Okay, to save space, we often use the condensed. This is probably the most popular type of formula that you'll be drawing. All that changes is now instead of putting all the H's around, you still show like the main overall chain, but now the H's are just going beside each carbon. Okay, the simplest that still shows all the bonds is the line structural formula. So basically for the line structural formula, okay, it represents at the end of each line is a carbon and it's bonded to the correct amount of hydrogens, whatever it might be. And so for these ones, the big thing is make sure to show like there's a carbon here, you have to bend it going down. And so you kind of just draw a zigzag line. Okay, so naming alkanes. Okay, the IUPAC, again, IUPAC just stands for International Union of Pure and Applied Chemistry. They're kind of the overall people that come up with these names. So that's when we're teaching you these names. They're the ones that came up with the system. Okay, these are the names you have to kind of learn or how to name. And if you learn naming alkanes, it'll help you naming everything that we kind of move on to. Okay, so each organic compound has three basic parts. A root, so the main part of the name, a prefix, which goes before, and the suffix that comes after. Okay, so the root denotes the number of carbons in the longest continuous chain of carbon atoms. The prefix gives the position and names of any branches coming off the main chain, and the suffix tells us what kind of family it belongs to. So for alkanes, the suffix is ane or ane. Okay, there is a root name for every possible chain of carbon atoms, but you only have to be responsible for learning the root names for the first 10. So we went over these again last year. Okay, 1 is meth, 2 is eth, 3 is prop, 4 is but. After that, they're the same as we learned. So pent, hex, hept, oct, non, and dec. And so you just kind of, so like these ones, you have your root name, meth, so 1 carbon, and then ane, it's all single bonds, so it's a methane. Okay, this one has 2 carbons, so it becomes eth. and then it has no branches coming off those carbons. So then we just put in the suffix ane. Okay, and propane is the next one.